We can start, right?
Yes, yes, yes.
Okay. Good afternoon, everyone. So today will be the last lecture of this lecture series by Professor Diganta Borah. And we have uploaded these lecture notes and problem sheets in our website. You can have it from there. And please raise your hands if you have any queries. So have a nice lecture today. Over to you, Diganta sir.
Thank you, Tavalla. Okay. All right. So today we'll try to wind up everything and try to at least complete the proof of the Riemann mapping theorem using the Dirichlet principle along the lines envisioned by Riemann. So yesterday, we introduced subharmonic functions, which are analog of convex functions, right? One variable convex functions. And we also learned the so-called maximum principle for subharmonic function. So one of its versions says that if you have a harmonic function that dominates a subharmonic function on the boundary, then it dominates inside also. So in view of this we learned that so subharmonic functions are basically, you can think of sub-solutions to the Dirichlet problem with a given boundary data. Okay. It can never be more than the solution if the solution exists. And in fact, we saw that if the solution exists, it has to be actually the upper envelope of all the sub-solutions, right? So let me quickly, recall some notations that I introduced yesterday. So let B be a bounded domain, and f from delta D to R a continuous function. So we are considering a family called Perron family. So members are the following. So a subharmonic function, if U is a subharmonic function, on V, and on the boundary, so if limit of U is not more than F, then we call, and U is called a subsolution. Okay? And the family of all subsolutions is denoted by PF. The family of all subsolutions is denoted by PF. This is called the Perron family. Corresponding to the given boundary data F. Okay. And we also introduced the Perron solution. So the function. So we define a function f tilde. This is simply the upper envelope of this family. So primum of users respectively using PF is called the Perron solution. So we stated the following theorem yesterday. With this Perron solution, F tilde is harmonic on D. So the Perron solution is always, harmonic. So only thing that can go wrong is that it may not achieve the boundary data that you started with. So it may not go to F as Z goes to delta D. We will see an example. Okay? So, but let's first take care of this. The F tilde is always harmonic on D. The proof is delicate, so we'll proceed step by step. First of all, you see, because harmonicity is a local property, so to show that F tilde is harmonic on D, enough to show that around each point in D, there is a disk where F tilde is harmonic, right? So we'll try to do that. So let D, A, comma, R, so this is a disk. This closure is suppose inside D. We'll show that. F tilde is harmonic on D. So here is your domain. So suppose this is your domain. Let's not make it very complicated. And you have a disk. This closure also lies in D, and I want to show that the function F tilde is harmonic on D. To start with, you see F tilde, we don't know anything. Even continuity is not clear. Okay, so we do not know anything. But what we'll do, we'll actually show that it agrees, it is equal to some harmonic function on this disk. That will imply that F tilde is harmonic. So for this, what I'm going to do, so let's pick a countable dense subset of this disk. So let Z1, Z2, and so on be a countable dense subset of D. And we'll show that that there is a harmonic function W on D. So let's give a name. Okay, so not let's call this disk. So I'll denote this disk by D naught. So D naught is equal to DAR. Okay, this will simplify our notation. So W on D naught says that W is equal to H tilde on D naught. Okay, so I am going to construct a harmonic function on this disk which agrees with H tilde. This will definitely prove that H tilde is harmonic on D naught. But see, now is suppose I already know that H tilde is continuous. No, I should actually. So first, what I'll do rather than showing just that instead of showing that it is equal to H on all of the so the first step is to show that just that W agrees with this H tilde along this sequence. This is what I will actually first assume. Okay, this harmonic function agrees with H tilde on this countable dense subset. Now you see, if I somehow know that H tilde is continuous, immediately I will be able to conclude that W and H tilde agree everywhere, right? Because this is a countable dense subset. If two continuous functions agree on this set, then they have to agree everywhere, right? But unfortunately, we do not know that. But I will take care of that, later. So first, let's try to achieve this. So here what you need to know is, so I started with a countable then subset. And my idea, IM is to show that the harmonic function, it's tilde agrees to some harmonic function on this. So the first step, I'm going to do the following. Recall that S tilde is the upper envelope, right? At each point, I define it as a supremum of UZ, where U comes from the Perron family. So for ZZ, I can actually, so because it is defined by supremum, I can find some sequence which converges to this is still a ZZ, right? So for ZZ, choose some sequence of functions U. So this is going to depend on the point Z. So I'm going to write ZK. Okay, so this is K from say 1 to infinity. So this is the sequence of functions in the Perron family. Such that S tilde of ZZ is equal to limit of UZK at Z. So that's K goes to infinity. For each Z, I am doing this. Okay, for each ZZ, we can do that. Now, this so you basically have a family of functions now. U, Z, K, right? Z and K both can vary. So it's slightly complicated. So I'm going to make it little convenient by doing the following. So so let's go to the next phase. So we have step 2. So what I'll do, I'll modify this sequence, gradually. So first step, I'll do the following. So let Vm be the maximum of UZK. So where 1 is less equal to Z, K is less equal to M. I am allowing Z and K both to vary, but finitely vary. Okay? So Z and K vary from 1 to M, and I'm looking at the maximum of this function, which I am denoting by Vm. So yesterday we also learned that if you have two subsolutions, then their maximum is also a subsolution, right? So this Vm is definitely in the Perron family, so it will not go out of that family. But VM has and also you see VM at ZZ, this will still converge to S tilde because being maximum, it is greater or equal to all these functions UZK, in particular UZM also. Okay. And so because now this is so of course being in the Perron family, this cannot be more than S tilde of ZZ because S tilde is the upper envelope, and this is converging to S tilde, right? So hence this in between guy also has to converge to. So therefore VM of ZZ. So this is M. So as M goes to infinity, okay? So this VM of ZZ converges to S tilde of ZZ. So this new sequence of functions or subsolutions will still converge at ZZ to S tilde. But what is good about VM is that it is actually VM is increasing. That is something new we have. VM is increasing, right? Because you see at every step, I'm taking maximum of more and more functions, right? For if you look at Vm plus 1, you will be taking maximum of use jk up to m plus 1. So you have the previous guys plus something more. So maximum of a bigger collection is more, right? So this is Vm is increasing. So this is something good. And it is still converging to as tilde along that countable sequence. Good. Third step. So I'm going to further modify this. My aim is to finally construct some harmonic function. So how I'm going to do? Well, if you look at the previous picture, so let's go to this picture. So I have a sequence now Vm. It is an increasing sequence of sub-solutions. And I know that they converge to S tilde along a countable dense subset. So these are these yellow points. Okay. What I'll do now, so Vm is this given this function. So what I'm going to do, I am going to consider the Poisson modification of Vm on the disk because I want to produce something harmonic, right? So I'll look at, so I'll call that function Wm. So Wm is equal to Vm here, and Wm is equal to the Poisson modification of Poisson integral of Vm on the boundary. So yesterday we introduced this Poisson modification. So this actually, produces a bigger subsolution, right? But which is harmonic now on the disk. So let's write it down. So let Wm be the Poisson modification of Vm on the disk DAR, which we denote by D. So what are the properties Vm have? So first of all, we know that Wm, this is still in the Perron family. Yesterday we proved this. So again, because you see Vm, so it is skews between Vm and right. This is bigger than Vm. We know that it's bigger than the previous thing, and then it is skews between Vm and S tilde of Z. Right? So this implies that this still converges to S tilde of Z because Vm. So Vm converges, right? The additional properties Wm has are, so let's see if it is still increasing. So you want to keep that property intact. Now you see Wm is Vm outside the disk. So Vm is increasing, so Wm also increased. What happens inside the disk? Well, if you look at here, well, Wm plus 1 on the boundary is Vm plus 1. But Vm plus 1 is greater or equal to Vm. So Wm plus 1 is bigger than Wm on the boundary of the disk. So by maximum principle, it will also be true inside, right? So maximum principle for harmonic functions. So this is actually still increasing. So Wm is increasing. But additionally, we also have that Wm is harmonic on D0. So what we have now is a family of, so you have a sequence, increasing sequence of sub-solutions. And good thing is that the sequence is harmonic inside the disk. So yesterday we learned that if you have a sequence of increasing sequence of harmonic functions, the Harnack's theorem implies that it converges uniformly on compacts, right, to a harmonic function. So by Harnack theorem, so Wm converges uniformly on compact subsets of D0, the harmonic function W on D0. Good. So now you see what we have. Thus, I have constructed a harmonic function W on D0. And what are the properties it has? Well, W at ZC, well, it is limit of Wm of ZZ, right? But this is also S tilde of ZZ. So this harmonic function W agrees with H tilde along this sequence. Okay, as I claimed, we can construct, so given a sequence, we can construct actually a harmonic function W which agrees with the Perron solution along this sequence. This is fantastic. But only thing is that I still cannot say that W and S tilde agree everywhere, right? Because I do not know if the function S tilde is continuous. Otherwise, I would have been immediately able to say this. But to take care of this, what I'm going to do, so let's look at the previous picture. So this yellow dots represents the sequence ZZ. But I want to show that these two functions agree, everywhere in that is. So let's pick up some arbitrary points that say, so let's call this Z naught. This is an arbitrary point. So now my claim is W is equal to H tilde on the naught. So let Z naught be an arbitrary point in this disk. So what I'm going to do, so I'm going to add this point to the previous sequence to get a new sequence. So consider the sequence Z naught, and all other elements are I do not change. Okay, so I have just adding this additional point to the sequence. Now my previous argument says that given such a sequence, this sequence is still countable as. So given this sequence, my previous argument says that I will be again able to construct some harmonic function which agrees with S tilde along this sequence. Of course, that new function may not be W, but definitely I can find some function, right? So by the previous argument, there exists a harmonic function maybe we should call it something else, maybe say W naught, such that this will agree with S tilde along the sequence ZZ, but now Z is greater or equal to 0. Okay, Z0 to Z0, Z1 and everything. So I have some additional point here. But then you see, now look at W naught ZZ. This is now S tilde of ZZ. And I know that this is also equal to W of ZZ. For Z, greater or equal to 1, right? But W naught and W, they're harmonic and so continuous. So W naught and W, they agree on a countable band subset, will immediately imply that W naught is equal to W on D naught, right? So this implies, now I wanted to show that W and it's still the agree, right? Everywhere. Z naught was the arbitrary point. So let's look at what is happening at it's still at Z naught. What I know that this is W naught at Z naught, but I have just proved that W naught is equal to W everywhere. So this is true. So therefore, S tilde is. So I have shown that S tilde is equal to W on D naught, and hence harmonic. Okay, so this completes the proof of the theorem that the Perron solution is always a harmonic function. Right. This is not very difficult because all the the requirement we have already established. Now, as I said, the only thing that can go wrong is that the solution actually may not converge to the boundary data. This is the only thing. However, if the boundary is nice, if you put certain conditions in the boundary, then we can easily take care of that. So to tackle this issue, I'm going to introduce the following.
Sir.
Yeah.
So
Yes.
instead of why you are taking countable density here, you in your proof there is you can take any density also instead of countable dense because all
Because no, see, I want to deal with sequences, right? Because I have a countable dense subset, I have a sequence of functions. This VM I am constructing, UZK. So if you take, if you do not take countable, then you don't get a sequence, right? You have it will be more complicated to deal with. Okay, that's why. So this taking a countable sequence gives us a countable sequence of functions. This VM.
Okay.
Yeah. All right. So here's the definition. Let D be a bounded domain. And zeta naught is a boundary point. So we have something like this. And you have, say, some point zeta naught here. That's right. A subharmonic varior at zeta naught. It's very, or simply varior at zeta naught is a subharmonic function U, which is defined possibly only near zeta naught. So maybe on some disk around zeta naught intersection. It need not be defined everywhere. It's a local thing. This is my DC. Let's call this radius say delta. So it's a subharmonic function U on the intersection some disk around zeta naught of radius delta for some delta greater than 0, such that it has the following property. So this is a function defined near zeta naught. I don't need to know it everywhere, but it should satisfy the following property. First of all, it should be negative. Okay. Second, UF. So limit UZ as Z going to zeta naught. This exists and equal to 0. Okay, this is second condition. So Z going to zeta naught. So this is from inside this region. Okay, the intersection, the disk where the function is defined, and zeta naught is the boundary point. And so at other points of the boundary, so for example, say somewhere here, you take any other point. Here, of course, the limit may not exist, but what I want is that the lim sup of UZ, Z going to zeta, this is again strictly negative for zeta here on delta D intersection this. So it's a negative subharmonic function. Sorry. At zeta naught, it has limit 0. And away from zeta naught, boundary values are actually strictly less than 0. It's like it is peaking at the point zeta naught. It has kind of the value at zeta naught is 0, and everywhere it is strictly smaller. Okay. So, and if a boundary point zeta naught is called a regular boundary point, or regular point, if there exists a barrier at zeta. So whenever there exists a barrier at some point, some boundary point, we call it a regular boundary point. Okay, so I'll give you some example, but before that, a remark. See, although I'm defining, or actually it is an easy exercise. So in our definition, barrier is something local. Okay, it is defined near the point zeta. But this exercise tells you that. So you can actually extend the function to all of the. Show that the barrier U above can be extended to all of the and satisfy, and it can be extended so that it satisfies so these three conditions I will write globally now. One is, of course, U is negative on the U is this anyway holds U z goes to 0 as z goes to zeta naught, and limits of z going to zeta, U of z is negative for zeta now, any boundary point other than this zeta naught. So extended means extended subharmonically, okay? So if you find a local barrier, you can actually globally, you can extend it to a global barrier. Okay, all these properties remains true, that it is subharmonic, it is negative, it goes to 0, and limits of is this is an easy exercise, so I just leave it to you to tackle this. Okay, so some examples should be good at this. Let's look at some very simple domains. So let's look at the unit disk. And let's look at, so this is the point 1. So let B is equal to the unit disk. And I want to show that this point 1 is a regular boundary point. You can immediately actually think of a barrier. In fact, so let use it with a function. Simply you take x minus 1. Sorry. So this is basically real part of z minus 1. Okay, so this is actually a harmonic function, right? U is real part of z minus 1, so it's a harmonic function. And you see it has all the properties that you want. So it is certainly negative because z is from the disk. Its absolute value is strictly less than 1. So real part of z minus 1 is the real part of z cannot be more than 1, right? So it's strictly so this is strictly negative. It goes to 0 at 1, and other boundary points also. This limit is strictly less than. It's actually continuous, no? So it is continuously. It's in fact it's less than. It can never reach 1, right? Because z has absolute value strictly less than 1, less equal to 1. So so this is the barrier. This that. So U is the barrier. Actually, given, so this is one is a regular boundary point. Given any other point, you can write down a barrier. There are two ways. One way is to simply, make a rotation so that it comes to 1. Okay, and then you compose with this barrier. That will give you a barrier. Or you can also, so if zeta is any other boundary point, you can actually check that. So for this zeta, you can look at, say, Vz to be, so I leave it to you to check real part of z bar into zeta minus 1. So check that this function serves as a barrier at this point. You can easily check this. Again, it's a harmonic function, right? Because z bar is an anti-holomorphic function, and then you are taking real part. Zeta is constant here. So this will be a barrier at zeta. So I wanted to consider some more examples, but keeping in mind that today we have to wrap up everything. So at this stage, rather than discussing more example, I'll go to the results that we want to prove, and if we have time, we will come back to see some more examples. Okay, otherwise I'll give you a set of exercise where we will see more examples of barrier and regular boundary points. So how does barrier help? So this is Theorem. So let D be a bounded domain, and zeta naught in delta D a regular boundary point. Okay. If f from delta D to R is a continuous function, then the Perron solution always converges to limit f tilde z as z going to this regular boundary point. It agrees. So zeta naught. So at regular boundary point, the Perron solution converges. And that's why this, you see, barriers are important. So if you can show that barrier exists everywhere, then the Dirichlet problem will always be solvable, no matter whatever boundary data you take, because the Perron solution always converges to the boundary data. It's harmonic, we have already seen. Now it's also, you can also claim that it takes the boundary value. Proof is simple. So let's try to quickly see this. So let's keep some pixels in mind. So we have some. So since this is zeta naught, which is a regular boundary point, right? So we want to prove that. So f. Let's do the following. So without loss of generality, we assume that first of all f of zeta naught is 0. This is, you see, you can simply make a translation by constant. So for an arbitrary function, you simply look at f minus f zeta naught. So then it will satisfy this condition. Okay. And I will also assume that the function f is bounded by 1. Okay. F is definitely bounded because it is given to be continuous on delta D, which is compact. So it's bounded. So you divide by the bound, so then it is less equal to 1. Okay. And if you prove the result for such a function, you can again reverse this process. So you can add back the constant that you subtract. You first multiply by the number that you divided, and then you add back the constant. So the original function will also satisfy this condition. Okay, so you don't have. So you can, without loss of generality, we can assume this. So we want to prove. So we have to prove. So limit of f tilde z now as z going to zeta naught is f zeta naught is 0. So we have to prove this. Okay. It's only for convenient I am taking this substance. So how do I do this? So I'll use the epsilon delta method. So let epsilon greater than 0 be given. So I have to produce a delta such that if I am in a delta neighborhood of this point zeta naught and inside D, then f tilde here is not more than epsilon, right? Mod of f tilde is less than this. So to find this delta, first of all, so let's do the following. See, what I know is that f is continuous, right? F at zeta naught is continuous, and it is so it is 0. So since f is continuous at zeta naught, and by our assumption f zeta naught is 0, so there is some delta. There exists delta greater than 0, such that so mod of f zeta. So this function is defined only on the boundary. So zeta is on the boundary. So basically, if you look at this portion, so this is the delta this thing. And if you are looking at this part here, so on this part of the boundary, the function is not more than epsilon. So I can always find the delta like this. So that mod of f zeta is strictly less than epsilon for zeta in D intersection, sorry, delta D intersection this. So let's give a name to this. So I'll call this D naught. Okay. Delta. The intersection by continuity of f. So this I have. So what I'm going to show is that this delta, maybe after shrinking a little bit, will work. Okay. So this is given. I have to find a delta. I have some delta to work with, but possibly I have to modify this, and then I'll show that this will work. So now let's bring. So we have a subharmonic barrier at zeta naught, right? So let's bring into the picture. So let U be a subharmonic barrier at zeta naught. And by our remark, we actually can assume that it is defined out of this is defined and all of it. Okay, so let's write down the properties that we have in hand. So this is so the properties to call U is first of all negative in D, and U of Z converges to 0 as Z goes to zeta naught, and lim so as Z going to zeta, U of Z, this is always negative for zeta in delta D intersection minus at zeta naught it is 0, but from this it is strictly negative. Right, these are the properties of the barrier that this barrier U. Now you see, look at this property, this condition here, the condition 2. So this barrier converges to 0 as z goes to zeta naught. So if I somehow can, squeeze our the Perron solution f tilde between, say, u and 0, I'll be done, right? If I can show that f tilde is more than u, but not more than 0, for example, then because u is going to 0, it will push f tilde also to 0, and we'll be done. That's what our aim is to show, right? The f tilde converges to 0. So I'll keeping this idea in mind. So what I'll do, so this for the function u, it may not be true. The f tilde may not be more than u. But what I'll do, I'll show that after modifying u a little bit, we can actually skews f tilde, the Perron solution, between this modification of u, right, and something more. So that is what my next step will be. So what I'll do, so I have to so modify this u. So let's do the following. So note that this function u, if you look at, so u is, because it is subharmonic, it is continuous on D. So I want to look at the following part of the domain. So let's look at the complement of this grid disk. So I want to look at here. Let's use another color here. So the function u is continuous here up to this red part, right? So this, I want to consider this closed region. So this boundary circle and anything outside the disk, and then including this part. So let's not change the color, including rest of the with the boundary. So what is happening here? U is continuous here, and on the circle, this circular arc, you see, U is continuous and it's negative, right? And on the blue part of the boundary, it is lim sup is strictly less than 0. So you can always find. So note that on D bar minus this D naught, this function u is less equal to some negative number. Lim sup is negative, and it is negative on this arc. It's continuous also, so you can always find some negative number such that u is less equal to minus 1 for some. I leave it to you to check the details. Okay, so this you can always do. So now consider a new function v. This is equal to u by rho minus epsilon. So this function, so as I said, some modification of u. This is the modification that I was talking about. So I will try to show that the Perron solution is bigger than this v. So let's examine some properties of v. So v is certainly subharmonic, right? So this is a subharmonic function because u is so, and you have just divided by some positive number rho and subtracted some constant. What I'll show that its boundary values are not more than f. That will imply that this is a member of the Perron family, right? It is a sub-solution. So let's try to examine the boundary values. I have to go to the next page, but I will also require the speak set, but okay, no problem. So let's try to compute lim sup of lim sup of, say, z going to zeta v of z. So I want to compute this. So this is equal to So let's look, the definition of V is U by rho minus epsilon. So this lim sup would be lim sup of, so 1 upon rho into lim sup of U theta, and then you have a minus epsilon to take care of. So this is, so let's look at the picture here. So first let's take care of this portion. So let's take zeta from this part. Okay, so suppose zeta is here. So if zeta is here, because, so let's try to understand. So because you see, lim sup of U is less than 0, because it is a barrier, right? So lim sup of U is less than 0. So this would mean that if you look at this definition, so lim sup of V will be less than minus epsilon, okay? Because lim sup of U is less than 0. So so this is less equal to. So I'm going to consider two parts. Actually, let's write it. I will need more space here. So this guy is less equal to now. So on this, I am in this part now. So delta D intersection the disk D naught, right? So here, so zeta is coming from here. Then this is, as we have observed, this is actually less equal to minus epsilon. Okay. And the other part where we don't need this much. And the other part, which is basically delta D minus this D naught. So here you can say something more actually. Well, the function U actually is, so here in this part U is less than rho, right? Minus rho, right? Here we have found rho such that U is less equal to minus rho. So U bar rho is less than minus 1. So lim sup is less than minus 1, and then this minus epsilon is also there. So here you have something more. So my minus 1 minus epsilon on this part of the boundary. Okay. But also let's recall what are the boundary values of F here. So here, so on this part, so here, remember F at zeta naught was 0, and so mod F was small near zeta naught, right? In fact, we choose this. So here actually we choose this delta so that mod F is less than epsilon. So that means, so here mod F is less than epsilon. So F is bigger than minus epsilon on this part. And we also assume that that mod F is always bounded by 1. So if you look at other points, here all we can say is that mod F is equal to 1, right? At least, so we have basically F is bigger equal to minus 1. So let's put it here. So on this part of the boundary, minus epsilon is, F is between actually minus epsilon and epsilon. And so here, what I can say is that minus 1 is less than or equal to F. Okay. So you can clearly see that the boundary values of V are not more than F, right? F is bigger than, for example, on the first part, F is bigger than minus epsilon, and lim sup of B is less equal to minus. And on this part, it is minus 1 minus epsilon, whereas F is bigger than minus 1. So what we see, so lim sup of Z going to zeta Vz is less equal to F zeta for all zeta in delta D. But this immediately implies that V is in the Perron family, right? It's a sub-solution because it's subharmonic and it satisfies this. Well, if that is the so, then therefore we have V is less equal to H tilde because Perron solution is the upper envelope, right? So it cannot be so, and V is a sub-solution, so the Perron solution has to be bigger than or equal to the bigger than or equal to this sub-solution. Now, so so now let's examine the limit. Now let's look at what is this limit. Limit of z going to zeta naught v of z. We modified this, so we don't have 0 probably, but let's go back and see what is this. Yeah, so v is here, u by rho minus epsilon. U goes to 0 when z goes to zeta naught, right? So that means v will go to minus epsilon. Okay, so we have, because of our modification, all we have is now this is minus epsilon 0. But h tilde is more than v, right? So this would mean that if I take a very tiny neighborhood of say zeta naught, so let's go back to again this picture. So what is happening here is that so v is going to minus epsilon as z is going to zeta naught. So if I take a very small neighborhood of zeta naught, I can say that v is greater or equal to say minus 2 epsilon, right? It's going to minus epsilon, so it has to be bigger or equal to minus 2 epsilon. And h tilde is bigger than v, so h tilde will be also bigger or equal to minus 2 epsilon. So what I'll do, this delta, the earlier delta, either I keep take a new delta or just take a smaller neighbor. Okay, so I just say that shrinking delta. So taking delta smaller if necessary. I now take a smaller value of delta, which I can definitely do. We have h tilde of say this, because this is greater or equal to vz, is greater or equal to minus 2 epsilon for z in this this green, the intersection zero. All right. So recall, I wanted to prove that S tilde lies between some say epsilon minus epsilon and epsilon. What I have estimated is that S tilde is bigger than minus 2 epsilon. 2 is not a sorry. 2 is not a problem. We can take care of that. But we have basically one side, right? So S tilde is bigger or equal to minus 2 epsilon. What we also want is that S tilde is still less equal to plus 2 epsilon. That will do the purpose, right? But that's not difficult. So what you do, I remember I worked with this function f. F was any function, any continuous function. So I could have worked with this this function minus f. Okay. Sorry, no, this is not. I think I messed up this notation. So there is no h tilde. This is f tilde. Sorry. Yeah, please correct this notation if I have. So only solution involved is the Perron solution for it. Sorry. So this is f tilde. So did I use h here also? Doesn't look like. Okay. So this f tilde, yeah, it is greater or equal to minus 2 epsilon. I will show that f tilde is also less equal to 2 epsilon. So what you do now, we work with minus f. If you work with minus f, what you will get? So working with, so replacing f by minus f, you would receive minus f, the Perron solution of minus f is greater or equal to again minus 2 epsilon. Okay, this will not change. The function f is changed to minus. Now, see if I can take this minus out. If I know that the Perron solution of say minus f is Perron solution of minus of Perron solution of f, then the things had been fine, right? So I could have easily immediately said that tilde f is less equal to 2 epsilon. But unfortunately, I cannot say that. I do not know this. So what I will do the following. So this is, by the way, this is for z in the intersection d now. So, but what we certainly know, this is an exercise actually for you. So if you look at, so exercise is just the following. So if you look at Perron solution of some function, say f1, plus you look at the parent solution of F2. This is never more than the parent solution of F1 plus F2. Okay, this is an easy exercise. You just have to check from the definition. You pick up some member from the family of F1 and some another member from the family corresponding to F2, and you can actually get a member corresponding to F1 plus F2. And you check this. It's an easy thing from the definition. So I leave it to you. So, but this implies that you see now F tilde plus minus F tilde, this is less equal to. So the boundary function is now 0 tilde. 0 tilde is, so if your boundary values are 0, you have a solution, right? It is 0. 0 is the solution to the boundary value 0. So in this case, Perron solution will coincide with the solution. So this is 0. But this immediately says that F tilde is less equal to minus of F tilde. But now if you combine this is less equal to 2 epsilon. So for Z in, thus we have proved that mod of F tilde of Z is less equal to 2 epsilon for Z in the intersection Q. Okay, so given epsilon, we actually found this disk D naught where this holds. This immediately tells you that limit Z going to theta naught tilde Z is equal to F at theta. So this completes the proof of the theorem. So whenever you have a regular boundary point, the parent solution always converges. All right. Okay, so I need to take a break, maybe for 5 minutes, and then we'll resume. Okay. If you have questions, please ask. Okay, let's resume.
Yeah.
Okay, so we have all the tools now to attack the Riemann mapping theorem, and we'll prove it. So recall the statement is, so let D be a simply connected domain in C, and D is not all of C. Then D is biholomorphic to the unit disk. So we want to prove it using Riemann's ideas. So we saw on the first day that we can always assume D to be bounded, right? It is always possible to map because we saw that by looking at the considering the square root function, we can actually enlarge the complement of D, right? You can map D to a domain. Conformally, we can map D to a domain whose complement is large, and then we can in fact a disk fits inside that, and then you're looking at the inversion. You consider the inversion along that that disk, so that will take the domain inside the disk. So you can always map it into conformally to a bounded domain, and so we'll assume that. So without loss of standardization, assume. So in fact, let me check XR1. We assume D to be bounded. Okay. All right. Step one of this proof is to show that you can solve the Dirichlet problem. If you recall the motivation that we considered in the first lecture, going behind a Riemann's idea. So it basically shows that you have to solve certain Dirichlet problems, right? And the problem that at that time during Riemann was that it was not known whether you can solve the Dirichlet problem for any given boundary data and for any bounded simply connected. But we have all the tools now. We will use that. So I want to show that. So zeta naught in delta D, we prove that zeta naught is regular. So every boundary point is regular, and hence the Dirichlet problem will be solvable, right? That's the theorem we have proved. That's what it says. So I need to take 1 minute, 1 or 2 minutes break because my battery of the pencil is it's a drained out, so I need to charge.
Yeah, sure.
Okay. Okay, hope we have enough. Okay, let's try this. Let's try to show that this zeta naught is a regular boundary point. So I'll draw some picture. So say this is your D, and some point. We're assuming this is bounded maybe, and you have some boundary point zeta naught. So first, let's look at the following function. The function, let's look at the function z minus zeta naught. This is non-vanishing, right? Because zeta naught is in the boundary, so this cannot vanish in D. The function, this is non-vanishing on B. D is also simply connected. So there is a branch of logarithm of this function, right? So there exists, therefore, since D is simply connected, so there exists a holomorphic Z on D, such that e to the power, say, Zz is equal to Z minus zeta. So you can clearly see that this function is 1, 1, right? Because if zz1 is zz2 exponentiating, we actually get z1 minus zeta naught equal to z2 minus zeta. We actually saw this in the first class also. So immediately, so let's write down these properties. So Z is injective. So that means Z maps D biholomorphically onto some domain ZD. So Z maps D biholomorphically onto ZD. So we'll now try to understand how do this domain GD, how does this domain GD looks like? Okay. So so let's look at the function G. Well, actually, let's take modulus on both sides. So this implies, so mod of e power zz is mod of z minus zeta naught, and this implies, so mod of e power z is simply e to the power real part of z, right? This is mod of z minus zeta naught, and so real part of zz is equal to log of mod of z minus zeta. Now you see, if z goes to zeta naught, so the right hand side goes to minus infinity, right? So real part of z goes to minus infinity. So if z goes to zeta naught, real part of g goes to minus infinity. So this domain ZD has to be unbounded. Yes, so ZD is unbounded. As real part of ZZ goes to minus infinity, as Z goes to zeta naught. This is an unbounded domain, but of course it goes to minus infinity, but it is bounded above, right? So this guy, if you see, because Z is coming from a bounded domain, so log of Z minus zeta naught. So mod of Z minus zeta naught is bounded above by some constant, right? So log is also bounded above. But as D is bounded real part of zz is less equal to, so this is log of z minus zeta naught. This is less equal to some constant, say a, for some constant a. So we can now draw a picture how ZD looks like. So you have some, say, some half plane. And your GD is going to be somewhere here. So this is real part of, say, real part of W is, say, equal to it. So here your GD will be something like, lies on the left of this. But the point minus infinity is on the boundary of, this domain. So I cannot draw this, but maybe I still mark it as, so say this is the point minus infinity. It's a wrong picture, but for the understanding, what we know that is on the boundary, right? Minus infinity, as we have seen here. So the picture looks like this. So Z maps. So this is your GD. Okay, so I have this map here. This map. So this is what's your D. Z maps D to this domain ZD, which picture is something like that. It is lies on this this half plane. But we know from complex analysis that I can map this half plane into the unit disk, right? I can, for example, this yellow line segment, not line segment, this yellow line I can map onto the circle, the unit circle, and I can also ensure that the left side goes to inside. So what I can do, I can consider now a transformation, say T, a Mobius transformation actually, T. This will take you to the unit disk. So this is one. And the domain will be, so where will this go? So you, in fact, you can write down, so I just write it down, you can verify. This map would be, so now I am, say, so this here variable is there, say, here it is a W. And then you have TW is, say, if I am not wrong. So go back and please check. So I might be wrong also. This is A minus 1, W plus A plus 1. Okay. So this map will actually, I hope it is correct. So, but nevertheless, you can check this. Okay, so this will take you inside the unit disk, and the point minus infinity will go to, you can divide both numerator and denominator by W, and then you can see that the point minus infinity will go to 1. Okay, so right, so the domain is going to look like something like this. Something like that. So this is T of, this is your T of C of T. But you see, we have already constructed a barrier for the unit disk at the point 1, right? So simply you have to look at the real part of, so let's call this, say, so the variable is, say, capital W here. So this is, here the variable is that, here W, and here is the capital W. So if you look at real part of W minus 1, that gives you a barrier, right? Or, so W is basically the composition of all this ones. So this is a barrier. So let me write it down. Yes. So first I applied G, and then I have what were the maps involved? G, and then this Mobius transformation T. So you have to look at so real part of TZ minus 1 is a barrier at zeta naught. So this concludes the first step. So zeta naught is a regular boundary point. So this is true for all boundary points, right? So the Dirichlet problem is solvable. So Riemann's envision, you see, he already like it was only incomplete at that time. It was not known, but nevertheless, his idea was completely correct, right? There was no mistake in that. So step 2 is to now again repeat what Riemann did. So now we know that the Dirichlet problem is solvable on D. So for simplicity, let me actually assume that. So this was the domain, and let me assume that the point 0 is inside the domain. Okay, this is not necessary, but only for simplicity. Okay, you can take some Z0. So assume without loss of generality. Assume 0 to be inside D. Yeah, you just make a translation, and then you can take Z0 to 0, and you once you map the translation to a conformally to a disk, and then this the original domain will also be. So this is not a problem. Now, if you recall from the first lecture, so in this case, so the boundary data that you want to consider is so let f of the notation I don't remember, but let's take maybe f zeta to be, or let's not use any notation. Okay, so let's consider the boundary data minus, it was something like minus z minus log of mod z minus z0. So z0 is 0 here. So I will consider this boundary data. Okay. And this is certainly continuous, right? Because zeta is non-zero. 0 is inside, so 0 cannot be on the boundary. You have some domain like this. Okay. So what I was doing, sorry, I now realize, because I'm working with a simply connected domain, I should not have drawn this. Okay, sorry. So this was a mistake. So I would have gone wrong somehow. Okay, so at this step itself, this step would have been not true if I didn't know that this is simply connected. Sorry, so this was a mistake. Okay, so no hole in the. Okay, so look at this boundary data. So by step 1. The Dirichlet problem on D is solvable. Let U be actually be we know that solution is unique. U be the solution. So U is a harmonic function on D, and it has boundary value minus log mod zeta. Then I'm basically reversing what I did in first lecture. So now let's look at the full. So first of all, let V be any harmonic conjugate of U. This exists because D is simply connected, right? So let's look at the function f of z to be. If you recall, we had something like z minus z0, but now I'll take z because z0 is 0, and then e to the power u plus iv. So this was the function that Riemann came up with, right? Only thing was existence of u was not clear at that time. So I'm now going to show that this function actually maps D conformally into the unit disk. Okay, definitely this is so. So what are the properties of f? F is certainly holomorphic, and f of 0 is 0, and you see f cannot vanish anywhere else because neither z nor the exponential part vanish at other points, right? So and f does not vanish anywhere else. So f maps 0 to 0. F is holomorphic. I still don't know it maps into the unit disk. We can check. So my claim is that mod of f is less than 1. Let's verify this. Then I would know that it is going inside the disk, right? How do I see this? Well, mod of f is that is from here. If you see, this is mod z into e to the power u, right? So I need to understand. So I want to show that this is less than 1. So what I have to show is that u is less than log of 1 by z, right? So that is u is less than minus log z. If I show this, then this right hand side will be less than 1. But you see, u is the solution to this. So this boundary, u is a harmonic function with this boundary data, right? So what? U is a harmonic function. You look at this function actually. Boundary data is log of this. So you look at u log of mod z. Let's look at this function. The function u is harmonic. Log mod z is subharmonic. That we saw, right? So this is subharmonic. On the and what happens on the boundary? Boundary u takes the value minus log mod z, right? So this is less equal to 0 and less equal to 0. In fact, equal to 0 on delta d. So you have a subharmonic function. On the boundary, it is 0. So inside it cannot be more than 0, right? So u plus log mod z, this is less equal to 0 in the, and so u is less equal to minus log mod z in the. Therefore, if you look at this equation here, e to the power, so this implies e to the power u is now less equal to 1 upon mod z, right? So therefore, mod of fz is less equal to 1. So this f, I should have strict inequality. There is, I think, so there are many ways to do that. First of all, f is a holomorphic. I do not yet know that f is forward, but nevertheless, this is, if you look at this inequality here, it has to be strict because if it is equal to 0 somewhere, the function has to be constant, right? But the function u is non-constant, right? So here it has to be strict. So inequality is strict. So I actually have, otherwise you have a constant function. U is not constant, that is clear. Log mod z cannot be constant, right? Boundary values are non-constant, so the function cannot be constant. So this is actually, you have strict. So this is otherwise constant. U is constant. Could be a contradiction. Okay. So this I can say that f is actually strictly less than 1. Right? So f maps the domain D into the unit disk. It goes 0 to 0 and no other point goes to 0. So for 0 in the unit disk, I have precisely 1 premise. But I see I need to show that f is 1, 1, 1, 2, right? So I have to show that for every point in the unit disk, there is precisely 1 premise. That's kind of not difficult. I will only outline how to do this. So we'll stop in maybe 2-3 minutes. So sorry for going beyond, but we also took a break, right? So all that is left to check is that f is 1, 1. So what you can do here is I'll simply draw a picture. So this was the domain D, say, and by means of this map f, so 0 is here. You have mapped it inside the unit disk. So this is 0. So I want to show that for every point, say W here, there is a pre-image that will prove it is surjective, and there is only one pre-image. And how do you show this? This is not this is an easy exercise actually, but I will nevertheless tell you. What you do, so this is the unit disk, so radius 1. So you now consider a circle like this, containing them.
Hello.
Yeah, we can't hear you. You need to unmute. You need to unmute.
Hello?
Yeah, now we can hear you.
Yeah. So till which part I was actually audible and visible?
The last 30 seconds were not there. We can't hear you. Yeah.
So this part was not there, right?
Your screen is gone. So can you please share again?
Oh, okay, sorry, yeah.
Yeah.
Huh. So this picture was there? Hello?
Yeah, can you explain this picture again?
Yeah, okay. So see, now our point is to show that the function f is 1, 1 and 1, 2. So what we do, so I take any w, this w here, and I want to show that there is precisely one pre-image. Okay, there is one pre-image that will, and there is only one. So for that, I am considering a circle or a disk of radius 1 minus epsilon containing this. And I'm looking at this rate domain d epsilon, which I'm defining to be z in d, such that is less than 1 minus epsilon. Okay. So here I just leave it as an exercise. It's an easy exercise. Apply argument principle. Okay. To on the domain on the epsilon. to see that fz minus w has exactly one solution. Once you write down the argument principle, this is basically here in this case, it is 1/2 pi I f prime by f minus w. You make a change of variable. You should go to the right side and immediately you will get this. Okay, solution to that's exactly one solution. Okay, this is true. This is true for all epsilon, sufficiently small. So it will eventually tell you that the function f has precisely one, w has precisely one premise. Since epsilon is arbitrary, w has precisely one premise. This proves that f is bisective, and hence the proof of the theorem is complete. Okay, that's it. And I'd like to stop here. Thank you. Am I audible or visible?
Yeah.
Okay. All right.
Yeah. Now, are you there? Okay. So, any questions from anyone in the audience?
Hello, sir.
Yeah.
Sir, is there any method to found the function between two? Can you found the function, sir? Is there any method for that we can found the function between them?
Sorry, I can't get your question. First of all, it's not. Yeah. So can you speak? Your voice is not clear actually.
Just like this is a bit.
What is?
Sir,
What is this? Okay, repeat it. Yeah. Okay.
My question is that, sir, that Riemann mapping first state that from every connected open subset of the complex set to the UDIS, we can found there exist a unique by holomorphic function. There exists a unique by holomorphic function between them. So is there any method that is there any method that we can found that function between them?
Is there any method so that what?
We can found that particular function about.
Oh, you mean how to construct? No, that's like extremely difficult. Okay, so only for some particular cases like half plane and some more domains. So for certain polygonal domains, you can write it down explicitly. Otherwise, it is not possible. Yeah, it's very hard. You don't have an explicit map. All you can say that there exists something. Okay.
Sir, I have, sir, two doubts in the problem set. Sir, what is the meaning of the normalization, sir? Question first. Normalization.
Where?
Inside problem
access. Normalization means I want to satisfy this extra condition. Okay, that's nothing more than that. No. So if you put those conditions, then the function is unique. So we just say normalize this means the function should satisfy this two extra condition. It's a polite way of saying that. Nothing more than that.
Okay. Also the symbol on the question for PDH. It is as a Poisson.
This is the right Poisson integral on the disk D. Yeah.
Also question 5 में सर जो D Z नोट R बार है सर वो हमारे पास सर का
so
वैसे ही सर मेरे पास
okay, which question is this? I actually have to open it, so I don't remember. Just give me a second so that I can open.
Okay.
So just 1 second. Question number. Which question?
Question 5th, sir.
Fifth question.
That symbol.
Okay,
So
yeah,
the
there's a
similar D
closer. That is for closer. Yeah. Right.
What is the meaning of the question number 7, sir? Oh, recurrent inequality is sharp. What is the meaning by that?
That means you see,
Question number 7.
for this, you cannot improve the bounds. So Harnack's inequality, if you look at the left side, the bound is 1 minus r by 1 plus r, right? Times HZ naught. And on the right side, 1 plus r by 1 minus r. So what I'm showing that you cannot improve the bound further. You cannot say, for example, upper bound, you cannot get something smaller because there is some function where the bound coincides with this. So this is kind of sharp bound. Yeah.
We can found better bound that bound.
Yeah. So this is kind of extremal. Okay, so you cannot find something. See, upper bound, if you can find some smaller upper bound, then that would have been an improvement. But this example shows that for this example, actually, their upper bound will match with whatever I have written. So you cannot find a better upper bound which works for all functions, right? So yeah, that is.
We consider that it is like supremum infimum, sir.
Say that again.
Supremum infimum, sir. Like that way.
No, but it is the supremum infimum of what? So it is just one number, right?
Okay. Like I'm trying the problem, sir. But not able to solve all of them.
No. You take your time and you keep trying. That's fine. I'll give some more exercise actually based on these two lectures. You should try. You can always contact me sometime if you want help. But if you try enough, you would be able to crack it. Okay. Yeah.
Thank you,
Sir,
Yes.
is the parent solution you constructed, it is unique or not, sir?
The Perron solution.
Yes.
Perron
Can you say
solution
anything? Can you say something about uniqueness or something?
See, Perron solution by definition is just a function, right? It cannot be, the question of uniqueness doesn't come. So because you are looking at a family of all subharmonic functions, and then you are looking at a supremum of this. So this is just function. So of course, there cannot be two Perron functions by definition. You are defining it to be supremum of a set. So it is unique, right? So you cannot be something else. Yeah.
Yeah. Any other questions?
Okay, so if no more questions, let us thank the speaker. And we will end with a vote of thanks by Amlan. Amlan, over to you.
So am I audible? Yeah. So first of all, I would like to thank Professor Diganta Borah to accept our invitation to be a speaker of this event and give such wonderful series of lectures. Thank you so much, sir. Next, I would like to thank Professor Satyanarayan Reddy, Professor Bhava Sharma, and Professor Chandrasekharan for their constant support throughout this event. As you all know that from the very initial days of CurryList, MTTS Trust has supported us in all possible ways. So I would like to thank MTTS Trust. Last but not the least, I thank the participants who joined us in the Zoom meeting, as well as those who joined in the live stream in the YouTube also. Thank you, everyone.
Yeah. Thank you very much. Let me stop the recording.